In this video, we're going to look at the transformations of functions. We're going to graph functions using vertical and horizontal shifts. We're going to graph functions with reflections about the x and y axis. We're going to determine whether or not there's compressions or stretches in the vertical and horizontal direction. We're going to combine transformations. And we're also going to determine whether or not the function is odd, even, or neither. So let's take a look at our first example. I have these three graphs. This is the equation of the graph, and this is the graph of that equation. And what do we notice about the graphs? Well, if I take a look at this first graph, what this point is this point that's been reflected. So I have x, y, I have negative xy. If I have 3, 4, I have negative 3, 4. And notice how the exponent on x is squared and I have a constant. If I take a look at this graph, it also seems to have this symmetry about the y-axis. If I have this point, I have 1 on the opposite side of the y-axis. I have that symmetry. Notice how the exponent is 6, 2, and I have a constant. Now the fact that I have a negative 3 and a positive 5 as coefficients, that doesn't really change the symmetry with respect to the y-axis. We'll take a look at this one. We have a negative 2 x to the 4th plus 4x squared plus 5. Once again, I seem to have the symmetry about the y-axis. I have an exponent of 4, 2, and I have a constant. So what do I notice? I notice that the degrees of the variables are all even, and I have a constant. And when that happens, I seem to have this symmetry with respect to the y-axis. Now let's take a look at our next example. For our next example, we have this graph. Now this graph doesn't seem to be symmetric about the y-axis, nor does it seem to be symmetric about the x-axis. However, what it looks like is that when I have this point up here, I seem to have this point directly opposite across from the origin. Notice I have that point directly across from the origin. If I have this point here, I seem to have this point over here directly across from the origin. If I take a look at this graph, it seems to have something similar. I have this point here, and I have this point here, directly across from the origin. This point here, directly across from the origin. Now notice on this graph, or this function and this function, that all of my exponents are odd. All of my exponents are odd, and there's no constant. I have x to the 7th, x to the 3rd, and x raised to the 1, x to the 3rd, and x to the 1, but there's no constant. Now, this brings us to what it means to be odd and even. So we say that a function is even if for every input we put in for x, we can put in a negative x and we get the exact same output. We say the function is odd if for every x that we put in, when we put in a negative x, we get the negative output. If it's an odd function, it's symmetric with the origin, just like the ones that I showed you in my second example. If it's even, then we say that we have symmetry with respect to the y-axis, like I showed you in my first example. So if I'm trying to determine whether or not these functions are odd, even, or neither, then what I do is I put in a negative x into the function and see whether or not my function changes, every single term changes sign, or if every single term stays exactly the same. So I'm going to do f of negative x, and I get negative 7, negative x, the quantity squared, plus 1. And I get negative 7, well, a negative x squared is just x squared plus 1. So this is even. If I take a look at my second example here, again, I'm going to put in a negative x. So g of negative x is equal to negative x plus 1 over negative x. So we get negative x minus 1 over x, and we can see that every single term changed sign. So we say that this is odd. Let's take a look at our last example. H of negative x is negative x raised to the 3rd power plus negative x, the quantity squared, which gives me negative x to the 3rd plus x squared. Now, my x to the 3rd became a negative x to the 3rd, but my x squared stayed a positive x squared. So this is a mix, and so we say this one is neither. Now you're thinking, Can I just figure that out? Well, sure. We know that if all of my exponents are even, if all my exponents are even and I have a constant, we can say that it's an even function, and we know that when I go to graph this, I'm going to have symmetry with respect to the y-axis. So all I have to do then is to find some points on one side or the other of the y-axis, and I just draw the other side because of the symmetry. On this one, now this one's a little different because it is x, which is a power of 1, plus 1 over x. Well, that's the same thing as, let me write this the same thing as, x plus x raised to the negative 1. So you could almost say, well, this has an odd power and this one has a negative odd power, so I knew it was going to be negative, or I knew it was going to be odd. If we take a look at this one, and this is a power of 3, this is a power of 2, well, then we know this is a mix, so it has to be neither. Now that works when I have polynomials or even rational functions. It doesn't always work when I look into my trig functions. So I would recommend that at this point you make note of what it means to be odd and even by the definition up above. So make sure that you pay attention to that so you can have the odd and even by that definition. Now let's start talking about our shifts. The first one we're going to look at is a vertical shift. Now, sometimes you're going to see this as K, sometimes you're going to see this as D. I'm going to frequently, especially in my classes, I'll usually say G of X is equal to F of X plus D, and I use a capital D there. And what that D is a vertical shift. So if you see a parent function such as the squared function, if f of x is equal to x squared, that's my parent function, and g of x is equal to x squared plus 2, then we know that we have a vertical shift of positive 2. What that means is I'm going to take my parent function and just move it up 2 in the y direction. If I would have had g of x is equal to x squared minus 3, then we know that this would have been taking my parent function, the x squared, and dropping it, vertically shifting down 3. So give an example of a vertical shift and graph the function before and after the vertical shift. So let's go ahead and just draw the parent function of x squared. Now we know the x squared will go through 0, 0. We have 1, 1, negative 1, 1. We have 2, 4. We have negative 2, 4. And you're thinking, isn't this an even function? The answer is yes. So here's my parent function. Poorly drawn, by the way. F of x is equal to x squared. And I had a g of x is equal to x squared plus 2. What that does is it takes all of my points, which is 0, 0, is going to go up to 0, 2. The point 1, 1 is going to go here. The point negative 1, 1 is going to go here. And you can see it just moves all of my points up 2. My other one that I had, which was g of x is equal to x squared minus 3, just moves all of my points down 3. It's a vertical shift down. So I'm going to go down, that 0, 0 is going to go down to 0, negative 3. The 1, 1 is going to go to 1, negative 2. The negative 1 goes, negative 1, 1 goes to negative 1, negative 2. And you can see that shifts it all down 3. If we can do a horizontal or a vertical shift, then we must be able to do a horizontal shift. Now what you'll see, and what I like to use, is I like to use f of x, and then I like to use a c there. And the reason I like to use the c is because when I use trig transformations, I can easily change that into a phi, which is a phase shift. Now notice that when I have this plus c, it is actually going to go in the opposite direction of what you expect. So once again, I'm going to use the parent function because the parent function of being x squared is easy to work with. So I know it's going to go through 0, 0, 1, 1, negative. That is a terrible, terrible, terrible. Still can't draw it. It's a little bit better y-axis. And then it's going to go through 0, 0, and it's going to go through negative 1, 1, 2, 4, negative 2, 4. And so here we go. Here's my parent function. Here is f of x is equal to x squared. I'm going to do g of x. I'm going to do g of x is equal to f of x minus 2. So in other words, what I have is x minus 2, the quantity squared. Now this means that I'm going to go right 2. So I'm going to pick up all my points. I'm going to go right 2. So 0, 0 goes to 2, 0. The 1, 1 goes to 3, 1. And the negative 1, 1 goes to 1, 1. And so it's going to look something like that. Now, what happens when I have g of x is equal to f of x plus 3? Well, since I know it's going to go in the opposite direction, my g of x is equal to x plus 3, the quantity squared, which means I'm going to move over 3 to the left. So 1, 2, 3. So that point 0, 0 now goes to the point negative 3, 0. And all the other points, of course, shift over as well. So there's an example of my parent function and shifting left and right. Notice that you are going in the opposite direction of whatever this sign is. It makes you want to go to a negative, makes you think you want to go left, but it's really going right. And you're thinking, why is that? Well, if I asked you to solve for x, if I asked you to do x squared plus, or excuse me, x plus 3, the quantity squared, x plus 3, the quantity squared, and asked you to solve for it, you would take the square root of both sides, and so we get x plus 3 is equal to square root of 0, which is just 0. And then you would have solved for x, and so you would have said, well, when x is negative 3, my y, or my x value would be, my output would be 0. So it's always the opposite sign. So when you're asked to graph a transformation, the first thing you want to do is determine whether or not you have horizontal or vertical shifts, identify what those are, whether or not you're going to go up or down or left or right, and then apply the shifts to the graph as expected. Now, when you only have horizontal and vertical shifts, it doesn't matter the order in which you do it. For the most part, it doesn't really matter the order if you're really good at it, but I'm going to recommend an order in a little bit. The other thing that happens is a reflection. And if the reflection is outside the function, that means it's taken all of my outputs and it is reflecting across the x-axis because all my outputs are the opposite signs. That's this. Notice it is outside the function, so it's going to do a vertical reflection. If it's inside the function, then it's a horizontal reflection. In other words, I'm going to reflect over the y-axis. So again, I'm going to start with my parent function here. A little bit over y-axis. It's a little bit better. If f of x is equal to x squared and g of x is equal to negative x squared, the negative's on the outside, then let's graph the two. So 0, 0, 1, 1, 2, 4, negative 2, 4. Here's my parent function, and here's my reflected function. Okay, now for the parent function of being the x squared, because x squared is even, I won't be able to see the reflection in the horizontal direction because when I put in a negative x, it's just going to give me x squared. So what I'm going to use for my parent function instead is I'm going to use f of x is equal to x cubed. Make it easier to see my parent function transformation. 0, 0, 1, 1, negative 1, negative 1, 2 and 8, way up there, and 2. So it's going to look something like this. Now, g of x is going to be negative x, the quantity cubed, which is going to give me negative x cubed. So this side is going to come over here, and this side is going to come over here, and it's going to look something like this. Now, you're thinking, but isn't that just a reflection across the x-axis? And the answer is yes, because x cubed is an odd function, and so it's going to behave as if I would have just done a reflection across the x-axis. But really what I did there was I did a reflection across the y-axis. So how do you do this? Well, if it's a reflection across the x-axis, you just take all of your x or all your y values, all your outputs, and multiply them by negative 1. if it's a reflection across the y-axis. You take all your x's and multiply them, your x values, and multiply them by -1, and then determine what the output is based on that new value. The next thing we're going to look at is compressions and stretches. Now this I always use an A, so I have g of x, and I use a capital A because that's going to lead us into, when we do trig functions, amplitude, when it's appropriate for the trig function, of f of x. Now, once again, this is outside of the function, and so it's going to affect the vertical, and it's going to do exactly what we expect it to do. So if a is greater than 1, it will be stretched. If a is between 0 and 1, it'll be compressed. And if a is less than 0, then it's going to be a combination of a vertical shrink, vertical stretch, or compression with a vertical reflection. So I'm going to give an example of a vertical stretch and an example of vertical compression of the graph. All right, so I'm going to use, again, I like to use f of x is equal to x squared. Then g of x, let me put g of x here in a different color. G of x is going to be, I'm going to first do my stretch, so I have 2x squared. So this time I'm going to move my graph down a little bit. And so I'm going to have an x squared, so we know we're going to 0, 0, 1, 1, 2, 4, -2, 4, and that's what that looks like. When I have the g of x, which is equal to 2x squared, all of my x's are going to, all my outputs are going to be multiplied by a factor of 2. So 0, 0 is not going to do anything. And this is where I'm going to take advantage of the whole even. I only have to do one side because I have a reflection, because this is an even function, on the other side. So I know that my first output, and this is the first time you're going to see me do this, is ordered pairs. So 0, 0 is my original ordered pair, 1, 1 is another ordered pair, and then of course 2, 4 is another ordered pair. This is outside my function, so I'm going to multiply all my y values by 2. So I'm going to do y times 2, 2y. Now, this is still 0, this is still 1, and this is still 4, or excuse me, 2. All my y's are going to be multiplied by 2. Well, 0 times 2 is still 0. 2 times 1 is 2, and 2 times 4 is 8. So these are where my key points for my parent function has gone to. And because of the fact that this is even, I know what the other side should look like as well. The other side, and when I'm talking about the other side, I'm talking about on the other side of the y-axis, would have been the ordered pair -1, 2 and -2, 8. So where did this go to? Well, let's go ahead and draw it. We still have the 0, 0, but now I have 1, 2, so I have 1, 2. That's not what I wanted to do. I have 1, 2, -1, 2, 2, 8, so 2, there's 4, 6, 8, 8, and then the one on the other side. So there is a vertical stretch. Now I'm going to do the same thing with the same parent function of x squared, just because it's easy to show you the compressions. And I am going to have my g of x now, so my g of x is going to be, I'm going to use 1/4 x squared. Now I'm going to make my grids a little bit bigger, so here's still my 0, 0, and I'm going to have this being 1 in each direction, and this is 2 in each direction, and this is 1 and 2, 3 and 4. So my parent function again is the ordered pair 0, 0, 1, 1, and 2, 4. Now remember, because of the fact this is an even function, I only have to do half of it because I have a reflection across the y-axis. And so I'll have 0, 0, 1, 1, -1, 1, and I'm going to have 2 and 4 and -2 and 4. So here's the graph of my parent function. Now, all of my y's are going to be 1/4 times y. So my x's don't change, so 0, 1, and 2. Excuse me, sorry. But my y's are all going to be multiplied by 1/4, so that's still going to be 0, but this is going to become 1/4, and this is going to become 1. Again, I have a reflection across the y-axis, so I only have to do the 1/2 because the other side will be a mirror image. So now I'm going to draw this, and so I'm going to go 1 1/4. So I'm going to go 1, and here's 1/4. So 1 and 1/4 is about right there. And then I have -1 and 1/4, and then I have 2 and 1, and -2 and 1. And so that is a vertical compression by 1/4. Okay, so you have to figure out what your vertical compression or stretch is, and then you just multiply all your y values by that vertical stretch or compression. Now we know that if a is a negative number, it will also reflect it across the x-axis. If a is between 0 and 1, then it's a compression, and if it's bigger than 1, it is a stretch. The horizontal stretches and compressions are sometimes a little bit harder to see, but what we're going to do is we're going to do the best we can with our parent functions. So I'm going to choose the absolute value. Now let's talk about what it looks like. If I have this multiplier on my x, the multiplier is not on my x, it's not in front, the multiplier is on my x, it's the b value. We're going to call this horizontal shrink or stretch based on what b is. Now, because it's inside my function, it's going to do the opposite of what we expect. So if it's a multiplier, we're actually going to divide. But if it's a fraction, we multiply by its reciprocal. And that's because what's happening is if my b is 3, then I would be dividing all my x values, because it's my domain change, by 3. If x was 1/2, then since I'm dividing by it, it would be the reciprocal multiplier, so it'd be 2, so it'd be twice as wide. Always the opposite of what you expect when it's inside your function. Okay, so let's do the parent function, and we'll do an absolute value. So this is the absolute value. I made this shape. The absolute value of x. So then g of x, I'm going to have this as 2x. So I'm going to draw my absolute value. And I go through 1, 1, 0, 0, negative 1, negative 1. I have 2, 2. And so here is my original function. There's the absolute value. And I can see that this is an even function because when I put in a negative x, I get the exact same thing as what I started out with. You can see that it's even. Now, so let's use some ordered pairs. So we're going to use 0, 0, and I'm going to choose, say, 2, 2, and I'm going to choose 4, 4. Now, this is a domain change, so I take all my x's and I'm going to divide by 2 because a multiplication is going on here, so I'm going to do the opposite of what's there. So the 0 for the y doesn't change, the 2 for the y doesn't change, and the 4 for the y doesn't change. Now what does change is all my x's are half. This is still 0, this is 1, this one is 2. And so I'm going to go 0, 0, that doesn't change. I'm going to go 1, and I'm going to go 2. And I'm going to go, because of it being an even function, I'm going to go -1 and +2, because I have that reflection across that y-axis. I have a mirror image. So then I'm going to have 2, 4, so I have 2, and then I'm going to go up 4, and -2, 4. And you can see that this graph has been compressed in from the original graph. So I'm going to use the absolute value again. So f of x is equal to the absolute value of x. And now I'm going to say that g of x is going to be the absolute value of 1/3 x, or you might see it more like x over 3. Okay. So again, I'm going to go ahead and draw my original parent function, which is the absolute value. It's going to look something like this. The ordered pairs, I'm going to use 0, 0. I'm going to use 1, 1, and I'm going to use 2, 2. So I take all of my x's, and I'm going to multiply by 1/3. So in other words, what I'm really doing is I'm taking all my x's and multiplying by 3, because it looks like I'm dividing by 3 right here, which means I must have to do the opposite. So I'm going to multiply by 3. So once again, I know that my y values aren't changing, so notice how I go ahead and write my y values as they are, and then I'm going to take all my x's and multiply by 3, so 0, 3, and 6. So I'm going to take my first point, which is 0, 0. I'm going to do 3, comma 1, and I have negative 3, comma 1, and then I have 6, comma 2, so I have 6, comma 2, 6, negative 2, and so here is my graph, and you can see what's happened is I've pushed my graph out, and it has stretched it by a factor of 3 in the horizontal direction. So, given a description of a function, sketch a horizontal compression. First, you want to make sure it's wrote in the correct form, and then you do the opposite of what you see because it is a division by that b value. So if you see a 3x, then you divide by 3. If you see 1/5 x, you multiply by 5. Let's combine the fractions, or the transformations. Now, when I'm doing the combination of the transformations, I'm going to go ahead and write, I have my parent function, and then g of x will be equal to, I'm going to use capital A, and then f of, I'm going to use capital B, x minus c, and then plus d. Now, the order doesn't matter if you do it correctly, but if you don't do it correctly, then you might want to pay attention to what the order I'm going to do. I'm going to do B first, and this is going to change the domain, which means all my x's are going to be changed. And I'm going to take all my x's by 1 over b. I'm going to do the absolute value so I don't have to worry about a reflection. Then I'm going to take my c. I'm going to do c second. So I'm going to do c second, b first, c second. And the c is going to change the domain by plus c or minus c. Just depends on if it's opposite. You're always going to do the opposite. So if this is a minus, then you're going to do a plus c or minus c. Depends on what's there. You always do the opposite. The next thing I'm going to do is my a. This is going to change the range. And so by multiplying your y values by whatever a is. And this will take care of the reflection as well. The last and final thing I'm going to do is d. This also changes the range by adding d or subtracting d. And this does exactly what we expect. So first I'm going to describe the transformation. Again, I'm going to start with b. I don't have a b, so I have this. So this is going to move. It's a minus, so I want to go left, but it goes the opposite, so it's going to move right 3. And then I'm going to do this. This is my d value, and so it's going to go down 5. So I'm going to take my absolute value function. I'm going to move right 3. So my vertex, which is 0, 0, is going to go positive 3. And then it's going to go down 5. 1, 2, 3, 4, 5. So here's where my vertex is. And I don't have any horizontal shrink or stretches or vertical shrink or stretches, so that is my graph. Now, let's take a look at B. Let's talk about all the pieces that happen. So the first thing that happens is my negative. So this means I reflect over the x-axis because it's a negative x. This 3 says I'm going to have a vertical stretch by a factor of 3, and this 1 means I'm going to go up 1. So the original square root function should look something like that, right? Should look something like that. Let's do our key points for this one, because sometimes I forget some of the key points for the square root. So the key points for the square root is 0, 0, 1, 1, 4, 2. Now, I'm going to take all my x's. My x's are going to be multiplied by -1 because that's my b value. And if I do a division by -1, it's the same thing as multiplying by -1. So this is still going to be 0 as the y, 1 for the y, and 2 for the y. So take my y, or take my x, which is 0, multiplied by -1. -1 times 1 is -1, and then -4. So boom, done with that one. Now I'm going to take all my y's and I'm going to multiply by 3. So all my y's are going to be 3 times as tall. So 0 doesn't change, -1 doesn't change, -4 doesn't change. All of my y's get multiplied by 3. So this is still 0. This becomes 3, and this becomes 6. The last thing I'm going to do is I'm going to take my y's and I'm going to add 1 to it. So my x's don't change, and my y's now become 1, 4, and 7. So these are some of my key points. They went from 0, 0 to 0, 1, 1, 1 to -1, 4, and 4, 2 to -4, 7. So what does this now look like? Well, let's put in the 0, 1. So here's my first key point. I have -1, and I go 1, 2, 3, 4, and then I have -4, 1, 2, 3, 4, and I need to go up 7. 1, 2, 3, 4, 5, 6, 7, and so here's what my graph looks like. Notice I did it by key points. I did it step by step. Key points makes it so much easier. So now, if I'm asked to write an equation for the graphed function, what I'm going to do is I'm going to think about what has changed. For this one, I have my vertex here. I'm still coming in with a slope of -1, and I'm still leaving with a slope of 1. All I have to do is just count the squares. So I know I have no horizontal or vertical shrink or stretches. So my A is going to be 1, and my B is going to be 1. The only thing that happened here is that I have moved to the right 3, so we know that's going to be x minus 3, and I've moved down 2, so that's -2. Now, on the next one, my key point should be 0, 0. Well, it's right there. My other key point should be 1, 1. Oh, so that doesn't look like there's any kind of vertical or horizontal shrink or compression or stretch. And then I should have 2. I should have 4, 2. So that one works, and then I have 1, 2, 3, 4. Oh, well, it still went over for up 2. Again, so that confirms that I have no horizontal compression or stretch, or vertical for that matter. So all I need to do then is do the movement. I went from 0, 0, I went down 1, and I went right 3, or excuse me, left 3. So my g of x is going to be the square root of x plus 3, that makes me go left, and then -1. Now on my last one, I have the quadratic. So first of all, this point went to here, so I know I'm going to move right 2. Now I have to look to see if my key points, if I go over 1, up 1, oh, over 1, up 1 is not working. Okay, so then I'm going to go over 1, 2, and up 2. Oh, okay, so my 1, 1 went to 2, 2. So I've got to deal with that 2, 2. So first of all, let's do the easy bit. We know that we move over that this g of x has to be x, and I'm moving to the left 2, so x minus 2, the quantity squared. Now, how do I deal with this? Well, I put in the point 1, 1, and it moved to 2, 2. So this and this. So it looks like what happens if I had a compression, maybe a compression of 1/2. So a compression of 1/2. Let's see if this works. If I put in the number 4, 4 minus 2 is 2. The quantity squared should be 4. 1, 2, 3. So I put in 4. So I get, oh, that should be 4. But if I have that compression of 1/2, then that works. I am squished it down by a factor of 1/2. Now they're asking me to write the equation of a function with this given characteristics. So here's the shape. So then I'm going to start that. I'm going to shift left 6 units. So I know this is going to be a +6 underneath the square root, and it's down 1, so it's a -1 outside of the square root. So it's going to be y is equal to the square root of x plus 6. That's my parent function, shifting left, and then down 1. I'm going to have a reflection. So upside down, it's going to be reflected across the x-axis. It's going to go right 2 units. Oh, so now I need to have a +2 in there. And it's going to go up 3, so it's a +3. And right means it should be a -2. Okay, so the reflection. So I have y is equal to, I need a negative out front to do that reflection. It is reflected across the x-axis. And then it's going to be x minus 2, the quantity cubed, because notice that the right 2 is inside the function, so it's inside the cubed part. And then I'm going to go up 3. Then we have our last one here. We have the shape of y is equal to 1 over x, but reflected across the x-axis, stretched vertically by a factor of 7, and right 1. The right 1 means that inside my function, I need to have a -1. That means it needs to go right there. That -1 needs to be right there, so it'd be x minus 1. I'm reflected over the x-axis, so I know that my a value is less than 0. So in other words, it's going to be a negative a value. And it's a vertical stretch by 7, so that tells me my a value happens to be -7. So then y is equal to -7, 1 over x minus 1. Now I can write this as -7 over x minus 1, and they're both going to be correct. So now let's bring it all together. And I'm going to do this by all the key points, and I'm going to do this step by step. First thing I'm going to do is this. Well, what does this do to my key points? So I'm going to take and write all my key points right here. I'm going to start from the left. -8, 3, -5, 0, -2, 3, 0, 3, 3, 0, and then 6, 3. I'm going to take all my x values. All my x's are going to be multiplied by the reciprocal because it's a division of -1/2, which means I'm going to multiply by -2. All my x's get multiplied by -2. Okay, so that means I'm going to write down all my y's. So 3, 0, 3, 3, 0, 3. And then I'm going to put in all my x's by multiplying by 2. So this becomes 16, this becomes 10, this becomes 4, 0, -6, and -12. So that does a reflection across the y-axis, and it does a vertical stretch. The second thing I'm going to do is I'm going to take all my x's and I'm going to add 1. So my next step is x plus 1. So once again, I have the 3, the 0, the 3, the 3, the 0, and the 3. All my x, notice I wrote all my y's down. And now I'm going to change all my x's by adding 1. So I'm going to have 17, 11, 1. Oh, I missed. That should be 5. So 5, 1, -5, and -11. I'm done with all my x's. I have finished with all my x's. So now I'm going to come outside and I'm going to deal with this -3. So I'm going to take my key points and I'm going to take my y's and multiply by -3. So this time I'm going to write all my x's. 17, 11, 5, 1, negative 5, and negative 11. All right, so take all my y's. 3 times negative 3 is negative 9, 0 is 0, then negative 9, then negative 9, then 0, then negative 9. And all I'm doing is I'm taking all of these y's and multiplying by negative 3 because that is what's telling me that I should be doing. This is the reflection across the x-axis. Now, my last and final thing is I'm going to take all my y's and I'm going to add 2 to them. My x's have stabilized. And now my y's, let me go ahead and put this other side of the parenthesis there. All my y's are going to add 2, so this becomes negative 7, this is 2, negative 7, negative 7, 2, and negative 7. Okay, so now I'm going to show you what happens. So if this is the point A now goes to a positive 17 and a negative 7. So because of my y values being the smallest y value is negative 7, the largest y value is 2, I'm going to just put my axes like this. So I need to go to negative 7 and 17. So I need to go to 17. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh, I've only got 12. So let's do this as 2. So 2, 4, 6, 8, 10, 12, 14, 16, 18. So here's where 18 is, right there. And I'm going to do the same scaling down in 2. So 2, 4, 6, 8, so right here. So here's where the point A went to. Here's my point B. My point B went to a 11, positive 2. So 2, 4, 6, 8, 10, 12, 14, 2, 4, 6, 8, 10, 11 is right there, and positive 2 is right there. So this is where the point B went to. And I need to move the A over just slightly because I am at 17, not 18. So that's where the point A went to. Now the point C, it went to 5, 7, negative 7, so 2, 4, 6, so negative 5 is right about there, negative 7. Here's where C went to, and in this region, on my original graph, you can see it is a kind of a parabolic shape. So I need to make sure I write a parabolic shape on those points. D, well, where did D go to? Well, D went to positive 1 and negative 7. So here's where D went to, and between C and D, it's a straight line. E, where did E go to? Well, E went to negative 5, 2, so 2, 4, 6, 5, negative 5, 2, so here's that. From D to E, it's a straight line, so here's where E is. And then my last key point, what we're going to call F. Where did F go? Well, the F went to negative 11, negative 7. So 2, 4, 6, 8, 10, 11, negative 7. And that's about where F went to. And notice I did it all by the key points, doing it in order. And then I labeled my points so I knew what the shape was going to be. Because I think if I wouldn't have, I may have tried to make that V shape when really the V shape is over there. And that's it for this video. I know it's kind of long, but there was a lot happening in this, and this is foundational transformations that you're going to see in a lot of your upper level math courses.